Energy use in the environment. I'm not going to test you on this section, but I think it's good to talk about it because it's a very current topic. So we estimate that every person in the United States uses over 100,000 kilowatt hours of energy per year. It's a lot. Where does it come from? A lot of it comes from the combustion of fossil fuels. And those are fuels that originate from ancient life. So we can look at chemical equations for the combustion of different types of fossil fuels. We can look at just pure carbon. We can look at methane, which is in natural gas. We can look at octane, which is a component of gasoline. Combustion reactions, they're all reacting with oxygen, and they're all forming carbon dioxide and water, except for this one, there's no hydrogen involved. And we can look at the standard heats of reaction for those different combustion reactions. So one way to look at, to evaluate fuels and say, well, this one's better for the environment and this one's worse for the environment, is to look at how much heat do you get in relationship to how much carbon dioxide is produced. Because we're trying to reduce the amount of carbon dioxide that's present, right? So if you look at that, you could do this per mole of carbon dioxide. So this would be per 1 mole, this would be per 1 mole. And so we can see that burning methane gives you more energy for the same amount of carbon dioxide production. So that's a better choice. This one would have to divide by 8. You can do the math, it ends up being smaller than the 802. So a better fuel has a higher ratio of heat production to carbon dioxide production. Fossil fuels, of course, are not renewable. Eventually we're going to use them up. It's estimated that we could deplete those in 50 to 100 years. It's kind of scary. This pie graph gives us an idea of where the fossil fuels are being consumed. So it's split relatively equally among residential, commercial, industrial, and transportation. Here's a graph of energy consumption over the years. So this graph starts in 1950 and goes up to when this book was, well, I think it goes up to 2013. Data lags a little bit behind. So we see that petroleum products consumption has been, increasing steadily. It went way up here and then it came back down again. Coal has kind of leveled off. Natural gas kind of came up and then it's been going down a little bit. And we've got renewable energy and nuclear electric power. So these nuclear electric power, while not technically a renewable energy source, it would take a really, really long time to run out of all of the fuel for that. That's just sort of interesting. So combustion generates carbon dioxide and water, and you say, well, what's bad about that? Well, nothing's so bad about that. Too much carbon dioxide isn't good. But what we're burning is not pure methane or pure octane. We could do that, but the cost of it is prohibitive, and the energy that we would use in purifying all of that is just not, it just doesn't do any good, doesn't make any sense. So there's additives and there's impurities in all of these fossil fuels. We also can have incomplete combustion. You probably, we hear about people dying of carbon monoxide poisoning. It's very tragic, especially since it's avoidable. But how does that even happen? Well, you've got a gas-burning appliance, and the intake of oxygen is not sufficient. So a blocked valve, something that didn't get cleaned, there's not enough oxygen being produced. The fuel will still burn, but it'll make carbon monoxide instead of carbon dioxide because there's not enough oxygen. Other things, sulfur-containing compounds also generate pollutants. So sulfur dioxide, carbon monoxide, nitrogen dioxide and ozone are 4 pollutants that are being monitored. The Clean Air Act is having a positive effect on our atmosphere, and we can see that we've got a percent change here of -81, -84, -60, and -33%. So all of these pollutants have declined between 1980 and 2013. So global climate change, and we just saw some new scary articles about this on Facebook. Carbon dioxide, that's where I get all my news. It's kind of sad. Carbon dioxide is a greenhouse gas. So the Earth is warm because it's surrounded by an atmosphere of gases. And carbon dioxide is one of the gases that when the heat from the sun comes in, it's allowed to pass through, but then so that's the light coming in, but then the heat that comes off of the Earth from that light is infrared light, and it's blocked by the carbon dioxide. And so it acts as an insulating blanket or like a greenhouse over your potted plants to protect them and keep them warm. So we need CO2, but we don't need too much CO2 or things are going to get too hot. And the CO2 levels in the atmosphere have been steadily increasing. Current observations suggest that the average global air temperature has risen 0.7 degrees in the past 100 years. And models suggest that if CO2 levels continue to rise, that this warming effect would just get worse and worse and could have disastrous implications for our planet. Oops, didn't mean to do that. So here's a graph showing carbon dioxide concentration parts per million in the atmosphere from back before 1860 up to 2013. And we see that it has risen. As the Earth gets warmer, then things start to happen like the glaciers melt and the sea level rises and all kinds of things happen. What is important to understand, though, is that this is data. And anytime someone shows you a graph, presents numbers and says, oh, look at this is terrifying. Well, where did the numbers come from? Data is data, but with statistics, we can manipulate the data and do lots of different things with it. And two people may genuinely believe that they're treating the data in the right way and come up with completely different conclusions from the same numbers. And so numbers, even though they're very concrete, they're also slippery. And you think about, well, how do you measure carbon dioxide concentration in 1860? Did they have weather stations set up all over the globe? No. Some of these measurements are indirect measurements. They can go back and look at the size of tree rings, the growth rings on trees, and various things like that. And then you have to ask yourself, well, how precise, how accurate are those measurements? Could there be some error there? There could be. Now, I'm not saying that global warming is not real. I personally have not taken the time to thoroughly investigate it. I think we should definitely try to reduce our CO2 production, but I also don't think that we need to panic about it. The average temperature of the Earth is not constant. It goes up and down in cycles, and we might just be on a normal up cycle, and it'll go down again later. I don't know. Nobody knows for sure. Any questions? Here's a problem we could do. What massive carbon dioxide in kilograms does the combustion of a 15-gallon tank of gasoline release into the atmosphere? Assume the gasoline is pure octane and that it has a density of 0.7 grams per milliliter. So we're burning octane, and that's going to make CO2. So we can write a chemical equation for that. So C, it's not a very good C. C8H18. What's the other reactant in a combustion reaction? Oxygen. Plus O2. And that's going to form what? Carbon dioxide and water. Do we need to balance this equation? Yeah, we do. Okay, 8 carbons. Put an 8 there, 8 carbons. 18 hydrogens. 2 hydrogens. If I multiply by 9, I'll get 18. And then we have to fix up the oxygens. So we've got O2 all by itself over here. We need to find out how many oxygens are over here. So we've got 2 times 8 is 16, plus 9. So that's 25 on the right side and only 2 on the left. What do we multiply 2 by to get 25? 25 halves, or 12 and a half. Do we have to use a fraction there? No, we don't have to. We could multiply. I told you about the odd-even problem. We'll just double everything and it goes away and you don't have to use a fraction. But we're not going to end up using the fraction in our calculation, so I'm just going to leave it alone. Okay, 15-gallon tank of gasoline, and we're saying that's octane. So 15 gallons of octane, density 0.70 grams per milliliter, and we want to know mass of carbon dioxide in kilograms. So this is a stoichiometry problem, but it's got all kinds of other things thrown into it. And so you need to be able to put pieces together and solve problems that you haven't seen before. And this is a sort of a problem that, could show up on an exam. Well, what do we start with? What do we start with for stoichiometry? We got the chemical equation, and then for the path, grams to moles to moles to grams, right? So let's maybe make a little space up here and start with that. Grams to moles to grams. And then we're going to look and see, well, do we need to change anything? Well, do we want to get to grams of carbon dioxide? We want kilograms of carbon dioxide. So we could just tack on an extra conversion factor at the end to get to kilograms of CO2, right? We're starting out with octane. Are we given grams of octane? No. We're given gallons of octane. So we've got gallons of octane. How do we get from a volume to a mass? Density. So if I had milliliters in here, gallons to milliliters, those are both volumes, and milliliters to grams is that density that was given. Now, if this was an exam, you'd have to be sure that you had the relationship between gallons and milliliters, which probably wouldn't be there, so there would have to be other conversions. But this isn't an exam, so I'm just going to ask Siri, because she's really helpful. So first we're going to get all the units in place. So 15 gallons of C8H18. I've got that path, that's the hard part. I'm going to follow the path. So I'm going gallons to milliliters, and gallons will be down there. And then I'm going to grams, and milliliters are going to be down there. And then I'm going to moles, and that's moles of octane still. Grams are going to be down there. Then I'm going to go to the moles of the other thing, moles of CO2, moles of octane down there. From moles, I'm going to grams of CO2, moles of CO2 down there, and then to kilograms of CO2, and grams down there. This is all dimensional analysis. We figure out how the unit trail goes. The path goes here, and then we just write it out in one really long equation. And we get all the units to work out, and then the units tell us where to put the numbers. Well, I don't know that one yet. How about grams per milliliter? That was given to me, the density. 0.70 grams per milliliter. So I'll write 0.70 with gram. And then I've got moles of octane in grams. Well, I need a molar mass, don't I? I can calculate that. 8 times the mass of oxygen plus 18 times the mass of hydrogen. 114.144. It's kind of a cool number. My starting number has 2 significant figures here, so I'm not going to worry about this. I'm just going to leave the whole thing. It's going to get rounded off to 2 anyway, and having extras along is not going to matter at all. So 1 mole of that is 114.144 grams. Here's my mole ratio, moles of carbon dioxide to moles of octane. 1 mole of octane generates 8 moles of CO2. 8 moles of CO2 for every 1 mole of octane. Here I need the molar mass of carbon dioxide. I've got that memorized, so 44.01. And then I've got the conversion between kilograms and grams. So I asked myself, well, what does kilo mean? Kilo means 10 to the 3. I've got kilo on the top, so I'm going to write what it means on the other side. So 1 kilogram is 1 times 10 to the 3rd grams. Kilo stands for times 10 to the 3rd. And then I'm just missing that milliliters to gallons. Hey Siri, how many milliliters in 1 gallon?
1 gallon is 3,785.41 milliliters.
Thank you. Okay, so that's a really big number. 3 where'd it go? Siri. 51, right? 3751.4. Pretty sure. Hey Siri, how many milliliters in 1 gallon?
1 gallon is 3,785.41 milliliters.
Thank you. 85.41. Oh, it's a good thing I checked. Because then it just disappears too fast. It's too quick for me. All right. Now we just take the numbers and stick them in. Go left to right, top to bottom, so that you don't forget anything. 15 times 3785.41 times 0.7 divided by 114.144 times 8 times 44.01 divided by 1 EE3 equals. So this equals 122.6 kilograms, not joules. 2 sig figs from the 15 gallons at the beginning. Can I round 122 to 12? No, that's ridiculous, right? 122, I'm rounding to the nearest 10, so that's 120 kilograms of CO2. Burning 1 15-gallon tank of gasoline. Of course, that's an estimate, right? Any questions? Renewable energy is something that people are actively researching for good reason. The sun is our biggest unlimited supply of energy, and so there are a lot of new technologies being developed to capture the energy from the sun. Solar power is one of the things that's become very popular here in California, where it's sunny most of the time, right? I have solar panels on my roof. They're awesome. Hydrogen-powered vehicles are a great idea. There's a hydrogen fuel cell. Hydrogen reacts with oxygen, forms water. There's no toxic byproducts or anything. What a great idea. Okay, the problem is, where do you get the hydrogen, right? Well, and hydrogen's dangerous, yeah. So you do need to be careful with the hydrogen because it is flammable. Well, where do you get the hydrogen? Well, you can get hydrogen from water. You can use this same reaction, but run backwards. You can take water and break it apart into hydrogen and oxygen, capture the hydrogen and power your car with that, and then as it powers your car, it reacts with oxygen in the air and it regenerates the water, so that's all awesome. But if you're using electricity from a petroleum combustion energy plant to get your hydrogen, then you're not helping the environment, are you? So what they're working on is using solar energy to decompose the water so that you can get the hydrogen without causing other problems. Of course, you know, all of this is very complicated because how much energy goes into making the solar panels and transporting them? And what about the disposal of the solar panels, right, once they're not useful anymore? So, very complicated situation. Solar power, hydroelectric power, and wind power are all renewable energy sources, meaning we're not going to run out of them. We're not going to run out of wind. Hydroelectric power is, you know, you've got a dam or just water flowing through a river, and you use the flow of the water to turn a wheel, and that can generate electricity.